So I had to upgrade my computer yesterday for security reasons, and it looks like it erased all of Zoom's settings, so I had to go back and reset them. So let's hopefully this will work now. And on top of that, I wanted to take a few minutes before regular class started to review, so I lost that time too. So let me get down to review then. All right, so the most of what I spent my lecture on last time, maybe it was too much, but I wanted to convey an intuitive understanding of what's involved in WKB approximation, especially in multidimensional problems where I think the picture is more vivid. Because I personally I consider the conceptual content of this whole approximation to be one of the most important aspects of the story. So let me try to go over it as quickly as possible. As a couple of pages here, which is mostly a review from last time. To take a specific wave equation, we'll take the Schrodinger equation for a particle moving in a potential in 3 dimensions, and supposing we're looking for an energy eigenfunction of an energy E. Now let's suppose we have a solution that has the form of a slowly varying amplitude times a rapidly varying phase. Slowly varying amplitude means the amplitude doesn't depend on h bar, or to put it another way, it means that the amplitude doesn't change very much over the extent of a de Broglie wavelength. I'll say more about that later on. This doesn't have to be an exact solution, just approximate is good enough, because right now we're just working on an intuitive picture. So if we draw the picture of the wave function in 2 dimensions, just make a 2D drawing, let's suppose it's XY plane. We draw the wave fronts, which are the contours of the function S and the exponent. Those are, we can visualize them as curves like this, representing a wave that's propagating in a certain direction. And associated with the wave is a moment. Each point on each wave front is a momentum, which is defined as the gradient of S, the action function that appears there in the exponent. We know that's a momentum function because if you look at the wave in a small region that's not too large, then the wave looks locally like a plane wave. And if you just use the plane wave relations, the de Broglie relations for the momentum of that plane wave, you get the P of X is equal to the gradient of S. That's where this comes from. Anyway, it's like a local momentum. So this leads us then to an interpretation, or rather an association, of a solution of the Schrodinger equation that looks like that, with an ensemble of classical particles. That is to say, at each point of configuration space where the wave exists, there also exists a value of the gradient of S, which we take to be a momentum. And we imagine that there's a particle, a classical particle there, with that X position and with the momentum given by P of X equals grad S. So that, in other words, configuration space is filled up with particles. Each particle at each point has its own position and its own momentum. We can think of this as a momentum field then, defining an ensemble of particles. The momentum field can be associated with the velocity field just by dividing by the mass. It's just classical relation now. And these are C number quantities here. It can also be associated with an energy, which is the kinetic energy plus a potential energy at the point X. Excuse me, was there a question? Okay, if there's no question, I'll continue. This gives rise also to an energy field, which is a function of X, nominally anyway, and any other quantity you can associate with these classical particles. Now that starts raising a bunch of questions once we've now got this picture. So to summarize, a solution of this form, the Schrodinger equation, leads to this classical picture with this momentum field and so on. So that leads to a bunch of questions. One of the questions is this: is that energy field, what's the relationship between that energy field and the energy eigenvalue of the original Schrodinger equation we were solving? Are they the same? The answer to that is yes, and I'll show you that in a little while in tonight's lecture. This energy field is actually constant and is equal to the energy eigenvalue of the corresponding Schrodinger equation. That means this momentum field that appears here has a property that p squared over 2m plus v at the x is constant everywhere. All right. Now then, here's another kind of question you can ask. Take this ensemble of particles. Let's take one of the particles, let's say that one right there at some time, and then let's let it flow under the classical motion, because you've got an initial position and momentum. It's a complete set of initial conditions for a classical orbit. Let that orbit flow, let it go for some period of time. This particle gets up and it moves somewhere else. Now, the place that it moves to, there used to be a particle there as well from the original ensemble, but when we turned on time, it moved yet to another place. So in other words, some old particle takes the place of some new particle. Now, when it does so, it ends up at the end of its trajectory with some momentum that came from solving the classical equations of motion. Question is that momentum the same as the momentum that was there already for the old particle coming from this field P of X? Question, you see. It's just a natural question that arises from thinking about these classical particles. And the answer to that question is yes, it does. It is. So what that means is that this momentum field is in effect a constant field, even though it's associated with particles that are allowed to move classically. Under the classical evolution, the field itself, the P of X field, remains constant. All right, I didn't prove that, but that's a property. And there's other questions one can ask too, and I'll come back to them. So how to address these questions in a quantitative answer is to take this Wkb form for the wave function, the slowly varying amplitude times the rapidly varying phase, and to plug it into the Schrodinger equation, which I kind of messed it up in writing it, but it's the same equation as above here. And to work on getting equations for the amplitude and phase, find equations for them. S is not really the phase. The phase is S over H bar. S is what you call the action, but you get equations for A and S. All right, that's the idea anyway. Now, if you do that, you substitute it in. I'll skip the algebra, but if you do it, some algebra, you work through it. What you find is that A and S have a dependence on H bar. They have a leading order term, which is independent of H bar, but there's higher order corrections. So to take those into account, you might want to expand A as A0 plus H bar H1 and so on, and do something similar for S. And if you do that, you get obviously a more complicated system. In any case, one in principle can do that and find higher order corrections to the A and the S. Now, there's an easier way of handling that, and it's a better approach, really. And the better approach says, let's bring the amplitude up into the exponent, just call the entire exponent W with a factor of I over H bar split off. So this is an exact substitution now for the Schrodinger, for the wave function psi. And then let's take the W and expand it in powers of H bar like that. And let's identify the W0, the leading order term, the H bar 0 term of W with S, because that's in other words, let's redefine S to be the H bar to the 0, the constant term of the W of the exponent W of the wave function. And as far as W1 is concerned, let's write it as minus IA times the log of the minus I times the log of the amplitude, because when you put that in here, you do the exponential and you bring the amplitude out. So these first two terms reproduce that ansatz we've got wrote down earlier, but there's now higher order corrections that one can work out explicitly. And what that means, if I go back to my original ansatz here, is that like this A times E to the IS, you now need to understand there's plus order H bar corrections to it. This is now only an approximation with higher order terms that are appearing there. Anyway, this makes it easy to do the algebra, easier to do the algebra. We just expand the W out in a power series like this. If this power series would converge, this would be an exact representation of psi. We're just expanding the logarithm of psi. Well, it's not a general psi because we're assuming the leading term goes like 1 over H bar. But with that assumption, it's otherwise exact, where the W0 is S and W1 is minus I log A. So we just go through the algebra of doing that. If psi is equal to e to the I over H bar W, we compute grad psi and then grad squared psi, work this out, plug this back into the Schrodinger equation. The kinetic energy is now proportional to psi, and the other two terms are proportional to psi too, so you can cancel them. And you end up with a boxed equation here, which is an equation for W. This is really nothing but a transformation of the Schrodinger equation from psi over to what is essentially the logarithm of psi, which is W. And I think that takes us up to where I left off at the end of the hour last time. This is now a new equation. It's equivalent to the Schrodinger equation. It's exactly equivalent. If you could solve this, you'd have an exact solution to the Schrodinger equation. All right. So before I go on, let me pause and ask if there's any questions about that, because that's a quick summary of what we did last time. It took me about 10 minutes to do it. All right. Yeah, it took me 10 minutes to do it. All right. If there's no questions, then I'll proceed. So to proceed, we take this grad W and we expand the W out in powers of H bar, and we take the del squared W and do the same thing here. And we get these, this is then the equation with the terms expanded out. We want to solve this order by order in powers of H bar. So allow me to go to a clean sheet of paper and do that. I'll do it like this. So if we take the H bar to the 0 power here, you can see the leading order term here is going to be 1/2m times the gradient of W0 quantity squared. That's a vector squared. That comes from up here. That's this leading term. The next term starts at order H bar, so it doesn't have any order H bar 0, so we skip that. And then the potential energy, V of x, and the total energy, E, are independent of H bar, so we just copy them down. If we go to the next power of H bar to the first power, then you get a cross term from the multiplication of this grad W0 and grad W1. So you get 1/2m, and the cross term is 2 grad W0 dotted into grad W1. And I'll cancel the factor of H bar that's in there because it's going to be a common factor. Then in the next term, we get an order H bar term. We get a minus I/2m times del squared W0, like that. And there is no order H bar term in the potential or the energy E, so that's equal to 0. So these are our two equations like that. And what we want to do is to put it into the more transparent notation. W0 is S and W1 is minus I log A. Let's do that. If I do that with the first equation here, what I get is gradient of S squared divided by 2m plus the potential V of x. This is all in 3D now, is equal to the energy E. And let me box that because, let me also switch over to a different pen. I try to do my lectures with a pen with a thicker point because it forces me to write in larger writing, which makes it easier for you to read it, I hope. In any case, we get this equation here at order H bar to the 0. And this equation is actually well known. It's been known since the 1840s. As a matter of fact, it's called the Hamilton-Jacobi equation. And there's a lot of history I could tell you about, but basically Jacobi improved on a method of Hamilton. And this involved a realization originally by Hamilton that if you could solve equations like this for this function, the scalar function S, it would be equivalent or allowed you to give a complete solution to the coupled differential equations of classical mechanics, so that actually 2n of them for the positions and momenta of the particles of the system. In any case, it has a long history, and then you get the Hamilton-Jacobi equation out this way. Notice, by the way, that this shows you that the energy field that I spoke of earlier actually is equal to the energy eigenvalue. That's exactly what this says if we identify gradient of S with the momentum. As far as the first order term is concerned, let's work on that a little bit. There's a common factor of a mass, which I'll cancel over here. The 2 cancels as well. So I'll do the grad W1 first. The grad of W1 is the same thing as grad of minus I log A. That's dotted into the grad of W0, which is the same thing as S. And then the second term is minus I/2 times del squared S, and that's equal to 0. Allow me to clean this equation up a little bit. First of all, the i's will cancel. The minus signs I can turn to plus signs. Grad log A is the same thing as grad A divided by A. So let me write this way. It's 1/A grad A dotted into grad S. That's the first term. And the second term is 1/2 del squared S equals 0. And now let's take this equation and let's multiply through by 2a squared, because if we do, the first term becomes 2a grad A dotted into grad S. And then we get plus a squared times del squared S equals 0. And if you look at that for a minute, that expression for a minute, you see that it's an exact divergence. It's a divergence of a squared grad S equals 0. And this is the most convenient form for the equation at order H bar to the first power. And this is given a name also. This is called the amplitude transport equation. All right, now, one of the reasons I'm going through this three-dimensional WKB analysis is that these equations have interesting interpretations in terms of this classical ensemble of particles that I was talking about. In the first place, I already explained why grad S should be interpreted as the momentum field. P is equal to grad S. And if you plug that in, you see you've essentially got the classical Hamiltonian P squared over 2m plus V of x. In fact, the Hamilton-Jacobi equation is sometimes written this way: as you take the classical Hamiltonian, in the x slot, you just put in the x variable. In the momentum slot, you put in the gradient of s, and you set that equals to E. And for more general Hamiltonians, this is how it always turns out to be. It looks like that. This is how, in fact, this is how Hamilton and Jacobi dealt with it. All right. Now about this del squared a squared del s, we have our wave function psi of x, which we now recognize is only approximately given by a of x times e to the I over h bar s of x, approximately because these are only the lowest order terms. There's actually a plus order h bar corrections that come in. I didn't go to h bar squared. I just stopped at the first two orders, but that's all you need for most of the interesting classical mechanics. So that's why I did it. But in any case, if we neglect this higher order corrections, then you see that psi squared is the same thing as the square of the amplitude. And this, of course, is the probability density as a function of x. It's the quantum probability density. And so that's what this a squared appearing in here is. By the way, if I take the del s and I divide it by the mass, that gives me the velocity, which is equal to the momentum divided by the mass. So I can do that. So the amplitude transport equation can also be written this way: as the divergence of rho times v is equal to 0. Well, the v you see here is the velocity of that classical ensemble of particles. If we interpret rho, which is really a quantum rho here, if we interpret that also as a classical rho, that is to say density of particles, then rho times v is actually a particle current. If I write J is equal to rho v, it's a particle current. It's a flux of particles. Particles, usual meaning of a flux. And so this turns into a statement that the divergence of that flux vector is equal to 0. It's actually a part of a continuity equation. There's no d rho dt here because we're dealing with a stationary state problem. So the rho is constant in time. But of course, what this del dot j equals 0 means is that if we imagine our ensemble of particles is not only particles that, at each point of space has a particle, but also it has a density. And the density is given by a squared that came from the quantum mechanics. Then what this equation is telling us is that the number of particles that flow into any given region in a certain amount of time is equal to the number that flow out. That's the meaning of del dot j equals 0. The flux in is equal to the flux out by Stokes' theorem or by Gauss's theorem. And so what this is saying is that the density of the particles is also stationary in time if you follow the particles by the classical flow, which is what this velocity v is. So these are all parts of the classical ensemble particle interpretation of the Wkb equations that come out of the three-dimensional Schrodinger equation for an eigenvalue problem in 3D. I'm going to enlarge this page a little bit to make it a little bit easier to read, and then reset it so that it's refocus it so that hopefully I can do that, refocus it.
One question, in the expansion, we'll have powers of h bar squared and then h bar cubed onwards.
Yes.
So do we just say that h bar is small, so we just ignore those?
We're only working to the first two orders here. So this is an approximation, and indeed all of WKB theory is an approximation. And it's an approximation that works more or less well depending on circumstances. As I explained earlier, you need the amplitude of the wave to change only by a small amount over a wavelength. Did I explain that? I meant to. Let me do it now then. Here, let me get this out of here. Let me get a new pad of paper here. So the idea that you've got wave fronts that look like this, and they have a certain wavelength lambda, it's a de Broglie wavelength lambda, which is equal to 2 pi h bar divided by the magnitude of the momentum. That's the same thing as 2 pi h bar divided by the gradient of s, the magnitude of that. That's just standard de Broglie relations. We require that the amplitude that appeared in the wave function, a of x e to the I over h bar s of x, be slowly varying. What that means is that lambda times the gradient of a divided by a is much less than 1. That means that the amplitude does not change much over a wavelength. You also require the same thing, for example, of the potential. The potential must also be slowly varying over a wavelength. And if this condition is not met, then this expansion in H bar is not going to work well. You see, if the idea is that H bar is small, but if the so in particular, one of the things that happens is that if the momentum goes to 0, then the wavelength goes to infinity. And so this picture where I've got nicely separated wavefronts like this breaks down, and it just isn't even qualitatively a good picture anymore. So there's an expansion here which can be thought of as an expansion in H bar, and we are indeed neglecting higher order terms. That's why this is an approximation. All right. Well, anyway, I think I've said most of what I want to say about the three-dimensional problem, and I'd like now to turn to 1D problems. The main reason for going through the 3D problem is the conceptual picture that it offers, and the fact that you get this nice continuity equation and so on, conserved current. It's more trivial in 1D and so a little bit less impressive. Nevertheless, the practical applications of WKB theory for actually doing computations are mostly one-dimensional. There are various obstacles to doing it in higher dimensions, not always. In any case, let's turn to 1D problems, which will be the main applications that we'll make. So in 1D, the gradient and divergence operators just get replaced by ddx. The Schrodinger equation itself just turns into the usual 1D equation, minus h bar squared over 2m psi double prime of x, plus the potential v of x times psi of x is equal to energy psi of x, the usual thing. That's the equation we want to solve now by WKB theory. The WKB ansatz is psi of x is an amplitude a of x times e to the I over h bar s of x, like this, and there's plus higher order terms. And the s of x is associated with momentum, p, which is going to be ds dx. Now it's a one-dimensional momentum. This is just transcribing the 3D relations we had earlier down to 1D. As far as the Hamilton-Jacobi equation is concerned, it turns into this. It's 1 over 2m times ds dx squared plus the potential energy v of x is equal to the energy E, like so. Let's solve the Hamilton-Jacobi equation, and then we'll work on the amplitude transport equation. So the first step in solving this is to just simply solve the Hamilton-Jacobi equation algebraically for the derivative ds dx. And if we do, you see there's a square. It comes in squared, so there's a 2 roots. It comes in with square root. You get plus and minus the square root of twice the mass times the energy minus v of x, like so. Now, the fact that this comes in with a plus and a minus sign means that there's actually 2 solutions S. S, you'll recall, is the action, which gives you the phase of the wave function. You can see that here. There's going to be 2 solutions, one with a plus sign, one with a minus sign. I think notationally, the easiest way of handling this is to throw away this plus or minus sign here and call the solution. We get just simply S of x. But to recognize that once we've got that solution, there's another solution obtained by replacing S of x by minus S of x. Let's do it that way, and then we'll get both solutions of the Hamilton-Jacobi equation. Having done that, then let's take this square root and let's notationally just define this to be p of x. This is a reasonable definition because you see this is the classical Hamiltonian here. And if we do this, then p of x is defined as that square root. And then s of x then is given by an integral from some lower limit to some upper limit of the, let me write it first of all this way, is p of x prime dx prime, which if you wanted to write it out explicitly, there's an upper limit x here. And then you get the square root of 2m times e minus v of x prime, and then a dx prime like this. Now the lower limit can be any value you want. Let me put it down as x0 like that. And you get a solution for s of x. the meaning of x0, if you think about it for a minute, is if I change x0, if I change the lower limit, it doesn't change the x dependence of s. That only affects the upper part. But what it does do, just add a constant to it. Well, adding a constant to s is the same thing as changing the phase of the wave function. So this lower limit of integration here is related to the phase of the solution. And let's say that matters of normalization and phase we're going to postpone. We'll worry about them later when we get the solution in better form. So right now, we can make this lower limit x0 anything we want. It just amounts to a phase convention. It is, however, worthwhile interpreting this p of x and this s of x. And let me now turn to an interpretation for that. To do that, let me go to a new page here. Let's take a specific problem. Let's say it is perhaps an oscillator. Draw potential energy like this. As a function of x, here's the potential v of x. Here's the potential, it's got a well. Let's say it's a well. I'll make the well lopsided. It doesn't have to be symmetrical about x goes to minus x. Let's put in an energy here like this. We get two turning points, a left one, which I'll call x sub L, and a right one I'll call x sub R, like so. And now what I'd like to draw below this is a phase space diagram. Now, of course, this potential energy can be interpreted classically. The classical orbit, classical particle, if we start at the left turning point, it slides down the hill, goes up to the right turning point, turns around and comes back again. And that's one cycle of the oscillator. Again, continuing with classical mechanics, we can describe this in phase space in the following way. Phase space is the space that has coordinates x and p, including the momentum. If I bring down these left and right turning points like this under the phase space diagram, allow me to do that, like so, then the orbit in phase space is an oval shaped thing, which, depending on my artistic skills, might look something like this. And it's symmetrical about the x-axis, which if I draw it right, it's going to look that way. See how well I can do it. So something like that. It's symmetrical about the x-axis because the kinetic energy goes like p squared. So p goes to minus p, doesn't change just basically reflects the curve up and down. All right. Now, what about this function p of x, which was p of x was a definition for ds dx. You put that in there. That's basically the classical Hamiltonian here. This is the orbit in phase space, and the particle goes in the direction indicated by the arrow. If you're in the upper half of this curve, the momentum, as you can see, is positive. And this motion along the upper half of the curve represents in this diagram, starting at that turning point and moving to the right where the momentum is positive. On the other hand, when the momentum goes down here, the momentum is negative and it takes you back to the original x place. This is the return path along the oscillator going back to the original starting point. So in phase space, the orbit goes around and around like that. The orbit, in fact, is a contour line of the Hamiltonian, classical Hamiltonian, which is p squared over 2m plus v of x. And in fact, it's that classical Hamiltonian set equal to the energy E. Well, the energy E, by the way, is the eigenvalue of the Schrodinger equation we started with here. And the reason it appears, the same E appears here, is because I'm telling you that in order to give a classical interpretation of the Wkb solution, we want to do that. We want to use the same energy E. But in any case, in classical mechanics, an orbit conserves energy. And so it has to be true that the orbit is actually the contour line of the Hamiltonian function in phase space. And that's just what I've got here. That's what it is. So this is the curve h equals e here in phase space.
Professor, could you clarify what are the subscripts on the turning points?
Yeah, it just means left and right, L and R. That's all it means, left and right turning points. Sorry, it's probably I probably didn't draw it big enough. That's what it is.
Yeah.
Okay. Okay, so now if I take some x value here, let me take an x value here like this, and I draw a dotted line like so. Looking in this potential curve, the particle passes twice, once going to the right and once going to the left. If I bring the same x value down to the phase space diagram like this, like so, coming on down, it intersects the orbit in 2 points, one there and one there. And that point right there has the coordinates x and p of x, where p of x is that x-dependent momentum function I keep talking about. Whereas I should make this thing point to the curve. It's the curve. What I want to point to that point there, this is has the coordinates x and minus p of x. This is to say it has a negative momentum for the particle going the other direction. So here's your interpretation of p of x and minus p of x. It's the coordinates of a point on the orbit. Now, what about the action function s, which is the integral of p of x dx? That's relative to some initial point. What's the interpretation of that? Well, let's draw an initial x0 here. Let me bring in another dotted line here and make an x0 right there. Let's call that x0. Well, between x0, so here's the x point. So between x0 and x, the curve here, which is really the orbit itself in phase space, actually is the function p of x. So the integral of p of x dx is nothing but the area under the curve, like that. And so that area right there, that area is the function s of x, measured relative to an initial starting point and then going over to the final place x, like this. So if I picture an orbit, a particle in the orbit, this isn't a particle going to the right now because it's got a positive momentum. As it moves along, the area under the curve increases, you see, as a function in time. And what that's saying to you is that in effect, the particle that's carrying the wave forward, its phase, the phase, it's as it's moving according to the classical equations of motion, in some sense, that little particle has an integrator along with it. It integrates p dx. And what that gives us is s, which is divided by h bar, is the phase of the wave function. So the phase of the wave function is increasing as the particle moves along here, along this direction, and the increase is the area under the curve. When the particle passes through the turning point and comes back down the negative side, the area continues to increase and goes all the way around until it comes back to its starting point, and then the total area is actually the area of the orbit itself. Well, all right. Anyway, this then gives you an interpretation of these functions p of x and s of x in this 1D problem. What now about the amplitude transport equation? If I take the amplitude transport equation and transcribe it to 1D, did I do that already? I forget if I did, but it's easy enough to do. It is going to be the del dot just turns into d dx. The amplitude squared is still there, a squared, and the gradient of s just turns into ds dx. So this is the amplitude transport equation in one dimension. Now then, the a squared, as I explained earlier, is the quantum probability, because it's the square of the wave function. Psi squared is equal to a squared, at least to the order in which we're working. And the ds dx, of course, is the momentum. So it says that the derivative of this thing is equal to 0. So therefore, a squared times p of x is equal to a constant independent of x. And so what you get is that a is another constant here divided by the square root of the momentum p of x, like so. All right. Now, this is not necessarily the same constant. The constant that appears here is really just related to the normalization of the wave function, because it's the amplitude times the phase as our wave function. So again, let's worry about normalization and phase later, and we can set this constant equal to anything we want. The main point here is the amplitude goes as the inverse square root of this momentum function. So that means that where the particle is traveling more quickly, the amplitude of the wave is lower, and that was shown in the harmonic oscillator solutions that I showed you in last week's lecture. Excuse me, in Tuesday's lecture. All right. Now, is there similarly a classical interpretation of this amplitude? And the answer is yes. Let's see if I have room. Let me tear the paper off because I may not have room to complete the construction. Let me draw the phase space orbit once again to get a clean picture, and put in the axes here like this. Let's say x and p. Momentum axis doesn't have to be in the middle. Let's consider a small interval delta x around some x point here like this, delta x. I wanted to find what I'm going to call a classical probability distribution, rho classical of x. It's classical because it's defined purely classically. And I'll say it in words first. The probability distribution is defined in the following way, so that the probability of finding the particle in some small interval delta x, or in any interval really, the probability of finding the particle in some interval is equal to the fraction of the time that the particle spends on that interval as it goes around its orbit. So if I take rho classical of x delta x, that's the probability of being on that small interval. Well, the particle passes through that interval twice, once going to the right and once going to the left. Let's let capital T be the period of the orbit, of the classical orbit. Now, this is all classical here. So this is supposed to be the fraction of time. So it's 1 over t multiplied times the amount of time that the particle spends in the interval. Well, that's 2 delta t. If I count delta t as the time it takes to cross this interval, we have a factor of 2 because it crosses it twice. So that's what this is. But that's the same thing as 2 over capital T. And the delta t, let me write it as delta x divided by the velocity v, where the velocity v is either to the right or to the left. Its magnitude is the same, it won't matter which one I do. It's the same for both of them. This in turn I can write by multiplying and dividing by the mass. I can convert that velocity into the momentum, and I get 2m divided by t delta x divided by the momentum p, which is naturally p of x. That's our x-dependent momentum. And so let me try to box this off because I made this diagram kind of too complicated here. But in any case, this is and I'm sorry I got buttons in the way. Let me pull it over so you can see. This then is elaborating on this classical definition of this probability density. Well, now the delta x's will cancel here. And to put the result, let me put it in some place over where we can see it. The result then is the classical probability density defined in such a way is 2m divided by the period t times 1 over the momentum p of x. Well, now look, lo and behold, that's what we got out of the amplitude transport equation. If a squared is the quantum probability, then the solution of the amplitude transport equation is saying that a squared is one over the momentum, or constant over the momentum. That's just what we're getting here. So what this is saying then is that the quantum probability distribution coincides with the classical probability distribution defined by saying it's the fraction of the time that the particle spends on an interval. Okay, so again, what I've done here is to give you not only a solution, now in just in 1D, of the amplitude transport equation, but an interpretation of what it means. And this is what it is. All right, so now let's do a real problem then on WKB theory. Let's solve a practical problem. We'll work on it anyway. It goes like this. Let's talk about a scattering problem. It's the simplest problem we can do. Let me have a potential energy here. Looks like this. Here's x, here's v of x. Let's suppose we have a barrier that starts off near 0 and then rises up continuously like this and then goes on, rises up to infinity like so. Let's suppose we send in particles from the left and at energy E. So the particles climb up on the potential hill, reach this turning point. There's only one of them now, but I'll call it XR here because it's the turning point to the right of this. The classically allowed region is to the left of the turning point. Anyway, just call it turning point XR. So classically, the particles climb up the hill, reach the turning point, and go back out again. There's an energy here, or quantum mechanically, there's an incident wave that comes in. It hits the well, it hits the barrier, bounces off, and comes back, and there's a reflected wave. That's the general picture of the problem that we'd like to solve. All right. Now then, there are two regions here, which I'll call 1 and 2. Region 1 is the classically allowed region, or CAR, classically allowed region. This is the region where the energy is greater than or equal to the potential energy V of x. And this region 2 is the classically forbidden region, CFR, where the energy is less than or equal to the V of x. We'll work in region 1 first because that's mainly what we've done so far is region 1 type things. So in region 1, let me summarize what we had before. We've got P of x is equal to the square root of 2m times the energy E minus V of x. I'm just copying things from an earlier page that I wrote. And we have an action function S of x, which is an integral of that. And the upper limit is x. And the lower limit, I'm going to make the turning point XR instead of some arbitrary x0. The reason for doing that is that I might as well, I need to choose something. So let's choose a point that has some meaning anyway. And so let's just make it XR. It won't, as I explained earlier, it really doesn't matter what the lower turning point is. But anyway, so this is going to be P of x prime dx prime. And I can write this out explicitly, of course, integral xr to x, the square root of 2m of e minus v of x prime dx prime, to make it explicit what S is. So let's make that definition for S. And the wave function in region 1 is going to consist of two waves. There's one that involves the plus S and plus P, and one that involves the minus S and the minus P from the two solutions. These correspond to really two classical ensembles, one which is moving to the right and one which is moving to the left. In effect, what we got is a wave that comes in, bounces, and comes back. You see, it's the incident reflected waves is what it is, the two solutions. These, of course, interfere with one another and give you oscillations in the sum of the two. The real solution is going to be a sum of them. So we need to take a linear combination of those two waves. Let me call the wave that's traveling to the right, let's give it a coefficient I'll call C sub r. And then the amplitude is 1 over the square root of the momentum. So I'll write as 1 over square root of P of x. And then we'll write this as e to the I over h bar s of x, like so. There's the phase. And then I'll leave a little space. And then the other one I'll call C sub L, where the L means traveling to the left. And the amplitude, again, is 1 over the square root of P of x. And then I have e to the minus I over h bar s of x. Now, I'm not quite done with this. Let me pull it over a little bit. I left some space here, as you can see. Strictly speaking, I should have put the square root of minus P of x in there, because in the solution that goes to the left, not only is S change sign, but P does also. If I wanted to bring the minus 1 out under the square root, I get a factor of I, the square root of minus 1, which I could then absorb into the coefficient C sub L. That's one of the things I could do just by redefining C sub L. I can make this formula okay with the same P with a plus sign as I had in the other term. What I'm going to do, though, is take that I factor that came out this way, and I'm going to split the phase, which is, of course, pi over 2. I'm going to split it between these two terms and put a minus I pi over 4 on that term and a plus I pi over 4 on that term. And if you like, I'm just doing that to take care of the phase that came from this negative momentum here, so that the denominators are now a common denominator. However, it's convenient to have this I pi over 4 factors taken out. It simplifies later algebra to do it, so I can justify it that way as well. It doesn't matter, since any sins we commit here can be absorbed into the CR and the CL. In any case, this is the structure of the wave function in the classically allowed region.
Professor.
Yes.
So when you introduce the allowed region and the forbidden region, you have greater than or equal to and less than or equal to.
Yes.
Which one is like? Because it's saying like technically when you're at v of x, you're in both.
Yeah,
so
that's the boundary right between them. That's right on the turning point.
Okay, so like, is that technically part of the forbidden region or the allowed region?
Well, it won't matter really. Maybe I should have just said greater than and strictly less than here. It would have been better probably.
Okay, I was just curious if there was like a distinction at that one point.
Yeah, no, I'm not trying to make any fine distinctions here. Let's just make it greater than here and less than there. That's better.
Okay, thank you.
Better anyway, yeah. All right, good. Now, in the classically forbidden region, we can still solve the Hamilton-Jacobian amplitude transport equations. The difference is that if E is less than V, then you see you got a square root of a negative number, so P becomes imaginary. So in region 2, let's make the following definitions. Let's define P of x is equal to I times the square root of 2m times V of x minus E. In effect, I'm choosing one of the two square roots. I could have made a plus or minus I. Let me just call it plus I as a convention. And then as far as the S of x is concerned, let's write this as I times what I'll call K of x, because S is going to be purely imaginary also, where K of x then is equal to the integral with an upper limit of x of the absolute value of P of x prime dx prime, like so. And again, let's make the lower limit the turning point xr. So integrate from there forward, you see, for this integral. It's an arbitrary lower limit. Let's just do it that way. And if you want to write this out explicitly, it's an integral from xr to x of the square root of 2m times v of x prime minus energy E dx prime, like so. All right. So there's going to be two solutions. IS, you see, is going to plus and minus IS is going to be plus and minus K. And so the solution then in region 2, we can write this way, is some coefficient I'll call C sub g, which I'll explain the g in a minute, divided by the square root of the absolute value of p of x. And then I'll write as e to the k of x over h bar. And then a second term, which is c sub, I'll call it c sub d, divided by the square root of absolute value of p of x, times e to the minus k of x over h bar. And let me box that because that's the solution in region 2. And again, for this absolute value of p of x, what I really should have put down is plus or minus I times this square root thing in there. But taking the square root of I and bringing it out and absorbing that into the CG and CD is something I'm allowed to do because these are just coefficients that I can use to absorb that. And so allow me to do that and write the solution in this form. If I do it, I have the advantage that these square roots that appear down here are strictly positive. And so, and not only that, but they're the same square roots on both sides. All right. So this is in an arbitrary linear combination of waves traveling to the right and traveling to the left in the classically allowed region. In the classically forbidden region, you may notice the function k, the integrand, is positive, and the final point x, which is over here in region 2, is greater than xr. So this, what this means, I'm sorry, I'm pointing to the wrong formula here. It's the k of x formula. The k of x, the integrand is positive. So what that means is that k is an increasing function of x. And so this term that has the k of x and the exponent, you see, is exponentially growing. That's what the g means. It means it is growing. So this is a term that's going to blow up exponentially in the classically forbidden region. The other term with the minus sign is damped. It's going to damp out over here. That's what the d means. This is the damp term. So this is a linear combination of growing and damped solutions. We'll keep them both for now because for general WKB problems, it turns out you need them both. All right, but in any case, here's our two solutions in these two regions. Now then, the Schrodinger equation is the second order differential equation in 1D, and so it has only two linearly independent solutions. And so it can only have two constants of integration in a general solution, not four. We have two here, CR and CL, and CG and CD. So there has to be some relations that connect this pair of constants with that pair of constants, the right and left, and the growing and the damped. And there are rules that give you these connections, and they're called connection rules. If you didn't know better, you might say that the way to get the connection rules is to extend the solution in region 1 up to the turning point, coming from the left, and then extend the region in the solution in region 2 back to the turning point coming from the right, and then just match them at the turning point, and that would give you connections, that would give you relations between the coefficients CL and CR and CG and CD. That, however, does not work, and the reason is that the WKB solutions are not valid at the turning point, nor are they valid in some small region around the turning point. This is evident from the formulas because the square root of momentum, which appears here in all the denominators, the momentum goes to 0 at the turning point. And so these nominal WKB solutions actually diverge there. They go to infinity. What's going wrong here? And this means that the solution is breaking down. It's actually not valid, as I say, in some small region around the turning point. What's going on here is that the WKB the approximation that's being made here is that the environment in which the wave is moving doesn't change much over the scale of a wavelength. But when the momentum goes to 0, the de Broglie relations tell you that the wavelength goes to infinity. So the wavelength is nominally infinite at the turning point. Now, it can't really be infinite because infinite wavelength would take up the entire x-axis, and there's only so much region around there. But it becomes big. As you get closer to the turning point, it gets as big as you want. And so the whole approximation scheme that the WKB theory is based on breaks down. And the result is that these formulas are not, none of these formulas are valid exactly at the turning point. Now, by the way, it is true that the wave function gets large at the turning point. Now, maybe I should make another point I didn't make earlier. I showed you earlier that the amplitude of x, when we solved the amplitude transport equation, was a constant divided by the square root of the momentum, the square root of the momentum p of x. That means that if I plot it here as a function of x here, and here's my turning points, let's say x right and x left, like so. by drawing dotted lines like this. In the amplitude function, you see diverges as the momentum goes to zero. It does this kind of a thing. This is what I was showing you in my previous lectures. This is the envelope for the oscillations that go between. And that envelope, you see, goes to infinity at the turning points because of this divergence of the momentum. Now that divergence is non-physical. The real wave function does not diverge there. But if you look at what the real wave function does, it actually has a rather high maximum there. It's maximum there, and then it dies off like this. So although it does not go to infinity, it does get large there. And also what you might call the wavelength also gets large. It gets the biggest lobe of all is right there at the turning points. So there is some indication that qualitatively, although not going to infinity, you get wide, large lobes at the turning points. All right. In any case, what this means is that in order to connect together these two solutions in the classically allowed and forbidden region, we need a separate solution in the turning point region itself. And so let me tell you about how we do that. How we do that, let me bring this picture down. How we do that is that, let me get it so that you can get it, emphasize it. The way to do it is to take this small turning point region here and to approximate the potential by a straight line over that small interval. So to go to a new page, here's how we do it. Let's take the Schrodinger equation minus h bar squared over 2m psi double prime. Psi double prime, let me write it explicitly, is d squared psi dx squared. And then for the potential energy, let me write it this way, as V evaluated at the turning point XR plus x minus XR times V prime of XR times psi of x is equal to the energy times psi of x. As I just explained, that means that in the neighborhood of the turning point where the energy meets it, we're replacing the potential by a straight line. And that's what this function is the straight line approximation, doing a Taylor series expansion of the potential about the turning point. Now the true potential evaluated at the turning point is equal to the energy over here. That's the definition of a turning point. So that term actually cancels that term. And we end up with minus h bar squared over 2m d squared psi dx squared plus x minus x turning point xr times v prime evaluated at xr times psi of x is equal to 0. This is an approximate Schrodinger equation in the neighborhood of the turning point. We can clean up this equation and simplify it by making a linear change of variables. Let's write x is equal to xr plus a constant a times a new variable we call z. We'll fix what a is in just a minute, but this is a linear transformation. And you can see that when x is equal to xp, which means you're at the turning point, this implies that z is equal to 0. If you substitute this into the Schrodinger equation and you choose the value of a properly, you can clean up the equation quite a bit and basically make a absorb all these constants that are in there. The nicest choice that works for this is to take a is equal to h bar squared over 2m times v prime of xr at the turning point to the 1/3 power. If you do the substitution and go through the algebra, then what you find is you get an equation that says d squared psi dz squared, where z is the new variable now, minus z times psi is equal to 0. And let me box that because this is the standard form of the Schrodinger equation in the neighborhood of a turning point, at least where the turning point is to the right of the classically allowed region, for almost any one-dimensional problem. This works for a wide variety of problems. All right. Okay, so this equation that I've created in this manner is one of the standard differential equations of mathematical physics. It's called Airy's differential equation. And it has two solutions. Being a second order equation, it has to have two linearly independent solutions. One of them is denoted ai of z, which everybody calls the Airy function. And the other one is denoted bi of z. And I don't know what everybody calls that one, but I call it the Berry function, so that we've got Airy and Berry. And I spell this, Airy's name is spelled A-I-R-Y, so I spell this one B-I-R-Y. But I don't know if anybody else in the universe does that. But anyway, let's call them Airy and Berry functions, where it's understood this is, Berry is not a person really. All right. anyway, as I said, these are two standard linearly independent solutions of this differential equation, and you can read about it in books like Abramowitz and Stegun on special functions. All right. So in the turning point region, the solution of the Schrodinger equation is given as a linear combination of AI of z and bi of z. What do these functions look like? Well, I'm glad you asked me, because I know you didn't really ask me, but I'm glad you would have asked me, because I have some plots of that. Here's a nice plot of the area function. So this is the z coordinate going over this way here. Let me put it there. There's the z coordinate, and here's z equals 0. So that's the turning point. And you see it's oscillatory to the left, and then it decays exponentially into the classically forbidden region to the right. You see it's got these nice oscillations here. You can see that the wavelength of the oscillations gets shorter as I move to greater negative z. And you see the amplitude decreases. There's a nice envelope to the amplitude right here. In fact, these are all features of WKB theory in general. This is WKB theory now applied to the area differential equation. Plus, you can see this large lobe here, which is right at the turning point, is wider than the others, and it's taller than the others. This is the wave function. This is the wave function acknowledgement of those infinities that occur in the nominal WKB solution. To understand the, so there's a lot of complicated formulas you can get out of the books on the area function and the Berry function. By the way, I'll show you what the Berry function looks like too. Here it is. The Berry function is very similar for negative z. It's got oscillations like the area function, but for positive z, it diverges to infinity rather than damping out exponentially. The difference between the area and the Berry is the Berry function diverges exponentially and the area function damps out exponentially. All right. Now you can look at the complicated formulas for the area and Berry functions and be bewildered by them, but if you understand a little bit of WKB theory, they're actually kind of obvious. The point to make, the first point to make is that if I go back to the area's differential equation, here it is. By the very way that we set this up, this is the solution. This is a Schrodinger equation for a particle and a potential, which is a linear function of x. We scaled it and normalized it to put it into a standard form. But there are physical problems where the potential really is a linear function of x. And for our problem, it's just an approximation in the neighborhood of the turning point. But for example, if you have a problem in a gravitational field, a particle moving in a gravitational field, potential energy V of x is equal to mgx. And so you see it's proportional to x. Well, with just a little bit of scaling of variables, that leads you directly into the area differential equation. So Airy's function, or the area equation, Airy's function is the solution, approximate solution of our turning point problem for our scattering problem in the neighborhood of the turning point. But it's also the exact solution for a particle in a gravitational field. And in fact, if we speak of the particle in the gravitational field, let's do it like this. It would look like this. If I call it x, like here in V of x, the potential energy looks like this. Let's suppose the true energy is equal to 0. So that means it's the same thing as the x-axis here, like this, and that means the turning point's at x equals 0. So what would that mean? That would mean that the particle is coming in. Let me do it here on, if I can do it in my hands. If you see my hands, the particle is climbing in the gravitational field. It reaches up to maximum, which is x equals 0. It turns around and goes back down again. On this diagram over here, that means it comes in, this wave that comes in like this, reaches the turning point, reflects and goes back again in the gravitational field. Now, as it falls in the gravitational field, of course, the momentum increases. That means the de Broglie wavelength is going to decrease. Well, that's just what you see here with the area function. You see, that's what's going on. That's why the wavelength is getting shorter. Also, I explained earlier, the amplitude goes as 1 over the square root of the momentum. That's relating the classical probability with the quantum probability. That's just what you're seeing here. So these formulas that you can dig up out of the standard references can all be interpreted basically in all this WKB sense with some simple understanding of what wave functions do and what classical mechanics does. So anyway, with all that prep, then I can give you quotations from Abramowitz and Stegun, asymptotic formulas of area and Berry functions, and here they are. Let me put this over here. here's the glorious formulas in all their grisly detail. Let me try to see if I can focus this better again. So there's two regions, the negative region where z is much less than 0. This is the classically allowed region. You see you've got sine and cosine functions for the area and Berry functions. That's where they both have oscillations there, but they're 90 degrees out of phase. The arguments here are the same. They look rather complicated, but there's this same pi over 4 that we saw in the Wkb formulas. You see basically the Hamiltonian is basically p squared plus z. That's the idea of it. If I strip off all the constants and stuff, that's the idea. We're setting the energy equal to 0. So the momentum p, you see, goes like the square root of minus z, like that. So what that means is the amplitude ought to go like minus z to the 1/4 power. And that's exactly what you see. Is exactly what it does do. Also, the phase s ought to go like the integral of p dz. Well, the integral of minus z is going to be minus 2/3 of quantity minus z to the 3/2 power. That's this funny looking expression here. That's where that came from. All right, so you can understand all the features of these complicated formulas. Basically, these are Wkb formulas. Likewise, over here is in the classically forbidden region. You've got the growing solution here with a plus sign for the Berry function and the exponent, and one with a minus sign for the Airy function. And again, you can understand the z to the 3/2 as being the integral of z to the 1/2, which gives you the momentum as a function of z. Okay, anyway, so this is all a way of saying that don't be afraid of these formulas. They all make sense. Now the rest of this then, the rest of this work, there's a fair amount of work that's involved here, because now what we've got is we've got a solution in region 1, some region like that. Then there's a turning point region, which is small. And then we've got region 2. And in region 1, we have two coefficients, c left and c right. And in region 2, we had two coefficients, c growing and c damped. And now in the turning point region, we got c airy and c Berry, ca and cb. So what we need to do is to use algebra, just a lot of algebra, to connect the left and right with the area and Berry coefficients, and then connect them to the growing and damped coefficients using all these asymptotic formulas. And you go through the algebra. And I'm not going to do it in lecture, but it's all the details are in the notes. And when you do that, you end up with a relationship. You can eliminate CA and CB, and you get relationships between the growing and damped and the left and right. Those are the connection rules, and that's what we need for practical calculations. So let me go back here and show you what the connection rules are. I summarize them down here. When you have a classically forbidden region to the right of a classically allowed region, as we do in this case, then the growing and damped are given in terms of the right and the left coefficients by this little matrix, and the inverse relation is here, obtained by inverting the matrix. This is CR and CL. I think, tell you what, I'm going to copy it again because I think I did it with a, here's the relations we want. CR and CL. I'll put it in bigger writing so you can see it better. After some work, we find the matrix connecting them in this form. C growing and C damped. All right. All right. Now. Okay. Now,
And so,
yes, question?
So these can be found by just setting the three solutions equal to each other at some point in region, at the boundary between region 1 and the turning point region, and between the turning point region and region 2?
That's right. We had a formula connecting the variable I called z with x. It was just a linear formula. And if you put that in there, you can see how the asymptotic form for the area and Berry functions connects with the WKB actions. It's no wonder, because one is integral p dx and the other one is integral of the scaled p times dz, you know. They're really the same integrals.
Mm.
So you put that in there, and then you can connect the area and Berry coefficients with the right and left coefficients on one side. Then you do something similar on the other side with the growing and damped. Connect those coefficients. Again, all the details is in the notes, and it's straightforward, but it's some algebra that takes some, you know, honestly, it takes an hour or something to go through it all.
Okay, so there isn't some like special X value where you set them to be
No.
equal to each other. Okay,
No. The asymptotic forms match together very nicely.
got it.
Okay. All right. And this
Does
gives us the
Does
connection.
the pi over 4 function also come from splitting the phase in the area functions?
When I was splitting the phase, I didn't need to do that because I could have absorbed that into the CR and the CL. So I did it just because I know it simplifies the algebra later on.
Where did but there was also a pi over 4 in the.
Indeed. And so now this raises the question of where did those asymptotic forms for Aryan-Berry functions come from? It did not come from WKB theory. It came from working with the integral representation of the Aryan-Berry functions and doing a steepest descent contour integration in the complex plane. This is really quite an interesting subject, but I think it's too far, afield from what we need to do here. If any of you want to hear about it, I'd be glad to tell you about it. It's actually very interesting how it works out. But that's where that came from. And in fact, if you look in the standard books on special functions, one of the main things you frequently want to know are asymptotic forms. You're usually interested in small argument values and large argument values. You probably know that already from the courses you've taken. But there's a question of where do those formulas come from? And typically they're done by steepest descent contour integration using integral representations, steepest descent in the complex plane. Does that answer your question?
Yeah, thank you.
Okay. From a more mundane standpoint, we just looked up the formulas in the book and we just used them. All right. In any case, this is what we've got. And then this down here is our picture here with the right and the left. Now for our picture, we want the coefficient of the growing solution in region 2 to be 0 because we want the wave function to die out once off to the right. The total wave function has to go to 0 and x goes to infinity. And so we want a solution in which c sub growing is equal to 0. And as far as c sub damped is concerned, we can set it equal to anything we want because it amounts to just the normalization of the wave function. And if we don't care about that right now, let's just set it equal to 1 because it's as convenient as anything else. So if we do that, then you can plug these in here. And what you find is that CR is equal to CL is equal to 1. And then that means then that the solution in region 1, which is probably the one we're most interested in, is going to be there's a common factor of 1 over the square root of the momentum P of x. And then we get e to the I over h bar s of x plus I pi over 4 plus actually its complex conjugate, e to the minus I over h bar s of x minus I pi over 4. All right. So this gives us a solution then for our scattering problem in region 1. Let me bring it up here so you can see better. It gives us a solution. We're mainly interested in region 1 because if you're an experimenter sending in beam particles at the target, the beam particles come in from the left like this. They hit the target, they bounce, and they come back. Now, scattering in 1D like this off of a barrier that goes to infinity is a fairly boring problem because all the particles you send in, all of them come back. They bounce back with there's a reflection probability is equal to 100%. On the other hand, this is a quantum problem, and there's an incident wave and there's a scattered wave. And those two waves interfere with one another and create an interference pattern. And that's something that's in principle is observable. So there is an issue about the phase shift between the incident wave and the scattered wave. And that's something which is, as I say, is physically observable. Now it's fairly trivial in a problem like this where I've got a barrier where you just get a simple reflection. But there are other one-dimensional problems where maybe the barrier turns over and there's a well that it can penetrate into. And there the phase or the interference between the incident and reflected wave becomes a much more interesting problem. And we'll see when we do scattering in 3 dimensions that phase shifts are really a big deal. So this subject of phase shifts is not out of place to talk about it here. So if we want to talk about phase shifts here, one of the ways of doing it is to define the incident wave with just the action s and not the pi over 4. It's really a convention to do that. But let me take either the I pi over 4 out out of this and just rewrite this in a fairly trivial way. Here's the denominator again. And let me take the first term as now e to the I over h bar s of x. And then for that, what that's going to do is double the phase here. It becomes minus I pi over 2. Let me write it this way as r times e to the minus 1 over minus I over h bar s of x, where r is equal to minus I, which is equal to e to the minus I pi over 2. And this will give this a name. We call this the reflection amplitude. So in a sense, what the reflection amplitude is it's the phase shift on the reflected wave relative to the incident wave. That's one way of saying it with this convention about what we mean by the incident reflected wave. You know, far to the left where the potential, assuming the potential goes to 0 as it normally does in a scattering problem, far to the left, both the incident and the reflected wave are just going to be free particle solutions. So then the R then is just the reflection amplitude. It's just a complex number relating the two. The fact that this complex number squared is equal to 1, this is what's normally defined as the reflection probability. And the reflection probability is equal to 1 here because all the particles you send in get reflected back. It's a trivial problem in that sense. Now so that's really all there is to solving this problem by WKB theory. It's not really very profound, but there's some interesting points that I want to make about this. An interesting point, at least. Let me make some space here. If I can go back to I keep bringing this picture back because I want to have this diagram here of the actual orbits and classical orbits in phase space and so on. We can visualize what's going on here, that as the particle comes in, climbs up the potential well like that, it integrates PDX to create the phase S of X of the incident wave. That's what that is. And then when it reflects and comes back out again, it's again integrating PDX, but P is now negative and the DX is negative, so PDX is still positive. And what that's doing is causing the wave to let's see here. What am I trying to say here? I'm sorry, I'm confusing myself here. Here's the idea. Here's what's confusing me. These formulas are actually slightly confusing because S of X is actually negative, and then it climbs up and reaches 0 at the turning point. And then beyond the turning point and coming on the return path, the phase is minus S of X, but that's now positive because S of X is still negative. That's because we chose XR as the origin of the integral for the phase function S. Okay, so the function S was defined as the integral PDX. And so far for our purposes, we've been thinking of S as a function of X. But it's natural to think of S as a function of time along the orbit. Let me do that and just write S of t for that. In which case, what I mean by this, let me write the integral again. What I mean by that is the integral of P of t along the orbit times dx dt along the orbit dt. You can think of it as a time integral. It's the same numerical value, but now you have a final time and an initial time t0. Let's do that. Well, if we do that, then you see the phase S of X started out negative, but increases towards 0 as you come to the turning point. That's in the upper branch. And then in the lower branch, it starts out at 0 at the turning point and continues to increase, again, because S of X is negative, minus S of X is positive, continues to increase as you reflect back outwards. That's just what this S of t is. However, because of this reflection amplitude R here, there's an extra phase shift of pi over 2 that came about on passing through the turning point. Now, in fact, the phase itself really isn't defined in the turning point region because the WKB version of the wave function breaks down. But you can think of the particle continuing in there, reaching the turning point, reflecting and coming back out, and continuing to integrate S of t along its orbit as if nothing happened. And when it reemerges from the turning point region, the wave function has a phase as it had coming into it, but now the phase has got this extra pi/2 phase shift, minus pi/2 phase shift attached to it. So people understand this intuitively, or one way of doing it is to say that when a particle passes through the turning point, particle in its orbit just runs through its orbit, integrating pdx and accumulating a phase of the corresponding wave function. But when it passes through the turning point, it accumulates an extra phase shift of minus pi/2. And that's a way of explaining the reflection amplitude in this problem. Now, then that's just an intuitive way of thinking about the WKB problem, but it has important consequences. Let's take the case of an oscillator. I'll draw the phase space portrait of an oscillator here. It's some kind of oval in phase space. It looks like this, and the orbit goes around like that. If I take some initial point on the orbit, then as the particle goes around, it integrates a phase integral of pdx, goes around the orbit like this and comes around, and then eventually comes back to where it started from. When it does, there's a total accumulated phase. And what is that? Well, it's 1 over h bar times the integral of pdx around the orbit. That's the loop integral of pdx. However, the particle also passed through 2 turning points, one on the left and one on the right, each of which gave an additional phase shift of minus pi/2. So there's a factor of 2 times minus pi/2 is the total phase on going around the orbit. This is an intuitive picture, but it accurately describes what's happening here. Now, the phase of the wave function, when it returns to where it started from, had better be equal to the initial phase, to within an integer multiple of 2 pi, or else the wave function will interfere destructively with itself. And what that means is we don't get a solution unless this quantity is an integer multiple of 2 pi, 2n pi, like so. All right. On the other hand, this loop integral pdx is otherwise the area of the orbit in phase space. It's the entire area. And so what we get here is a condition that the area in phase space is equal to n plus 1/2 times 2 pi h bar. I bring the h bar over to the other side. They gave me the 2 pi, and then the 2 times pi/2 is, of course, this becomes minus pi. That gave me the 1/2 here. We get n plus 1/2. So what this tells us is that unless the area of the orbit in phase space for an oscillator is n plus 1/2 times 2 pi h bar. By the way, h bar, Planck's constant, has dimensions of position times momentum. And so it has the same dimensions as area and phase space. And this is what these integrals are giving us here. So unless the area in phase space is n plus 1/2 times what you might regard as a unit cell or a unit quantity of area in phase space, 2 pi h bar, that's the same thing as Planck's original constant. He called it h. It's not h bar, came later. 2 pi h bar equals h. This is sometimes called a Planck cell. A Planck cell, am I still on the page here? A Planck cell in a one-dimensional problem is a region of phase space that has an area of 2 pi h bar. And so we're getting a quantization condition, and you can speak of quantized orbits. Those are the orbits that give you the quantization condition. The orbits have an area which is n plus 1/2 times a Planck cell. All right. The area of the orbit in phase space integral pdx in classical mechanics, pdx, let me do it right. The area of the orbit in phase space of a one-dimensional oscillator pdx like this, in classical mechanics, if we divide by 2 pi, is called the action and is sometimes given a symbol I. This is just a definition that comes from classical mechanics. It's just 1 over 2 pi times the area is all it is. However, the orbit in question, we need to know what the orbit is in order to do the integral, and the orbit in question depends on the energy. So this means that the action depends on the energy. And this can be inverted to give you the energy as a function of the action, and one oftentimes does this in classical mechanics. For example, you find that the frequency of the orbit omega is equal to the derivative dE dI, which is a theorem in classical mechanics that I won't prove now. But in any case, this is terminology from classical mechanics. So the quantization condition, which I expressed up above in terms of area, can also be expressed in terms of action. that I sub n is equal to n plus a half times h bar. Basically, the 2 pi factors cancel. And this is the quantization of the action of classical orbits for one-dimensional oscillators. The corresponding energy then gets quantized by saying that the nth energy level is equal to the energy action function evaluated at the nth quantized value of the action, like this. En is equal to E of In, like this. Okay? And this is called the Bohr-Sommerfeld quantization rule. This is the one-dimensional version of Bohr-Sommerfeld. Let's work it out for an example. Let's do the harmonic oscillator as an example, and then it'll be enough. We can quit for the evening. In the case of the harmonic oscillator, let me draw the phase space orbit, x and p. The phase space orbit for a harmonic oscillator is really an ellipse. I've been trying not to draw ellipses here necessarily, but for this is a very, very poor ellipse here. But anyway, it's supposed to be sent. Let me do it right. It's supposed to be centered. Like so. Here's x and p. The Hamiltonian is a p squared over 2m plus m omega squared x squared over 2. And if I have a definite energy E that I'm talking about here, then the x turning point here is obtained by setting the momentum equal to 0 and solving for x. So this gives me x is the square root of twice the energy divided by m omega squared. On the other hand, the momentum turning point right there is obtained by setting x equals to 0 and solving for p. And that gives me p is equal to the square root of 2me. Now this is relevant because the area of an ellipse is pi AB, where A and B are the semi-major and semi-minor axes. So for our ellipse here, this is pi times the square root of 2me times the square root of 2e divided by m omega squared. And if we put that together, what we get is 2 pi times e divided by omega. Now, according to Bohr and Sommerfeld, this should be equal to n plus a half times a Planck cell, which is 2 pi h bar. And so you see the 2 pi's cancel. And then we get the energy is equal to n plus a half times h bar omega. And this, of course, is the exact answer for the harmonic oscillator, showing you that Wkb theory for the harmonic oscillator gives you the exact answer. For the energy eigenvalues, it does. The wave functions are only approximate, and the energy eigenfunctions are energy eigenvalues are exact. Okay, well, I lost 10 minutes trying to take care of technical matters because I upgraded my computer yesterday, and of course, I had to do that. But anyway, that's enough for tonight. Are there any questions of what we've done tonight?
So we end up with the exact energy in this case. Is that kind of standard using this method, that you get close to exact energy, or is that special here?
The story is this: the WKB approximation is an approximation. And in general, it does not give you the exact answers for energy eigenvalues. As a practical matter, however, it oftentimes works remarkably well, even for the ground state. It's not supposed to, it's only supposed to work asymptotically for large n. But in fact, it tends to work quite well for many problems. The fact that it works exactly for the harmonic oscillators because of the special form, it's a quadratic function of x and p. You'd get the same, you'd get exact quantization for any quadratic functions of x and p that works. It works for them.
Okay.
But it's a rather special. In general, it's only an approximation.
Okay, thank you.
Yeah, are there any other questions?
I had kind of a notational question.
Yeah.
So a little like I think on the last page you were introducing the action. You called it I, and I was
Yeah.
wondering why you call it I instead of S. It's minor, but
Yeah, it's a good question. The reason is that there's a whole lot of different quantities in classical mechanics that are called the action,
okay.
and so the I here is 1/2 pi times the loop integral of p dx. So you see it's got dimensions of action p and x. The s was equal to the integral without a 2 pi of some lower limit, some upper limit, again of p dx. So you see they both have dimensions of action, but this one is an open integral, and this an open limit, and this is a closed one.
Okay, so
Okay.
the I is basically just to denote that it's like a closed integral.
That's, yeah, with the conventional factor of 2 pi here. There's a story in classical mechanics about why people do this. This is a member of what they call action angle variables. They're canonically conjugate variables. This I is like the momentum, which is conjugate to the angle. And,
Okay.
and in fact, this omega you see is equal to the angle dot, theta dot, theta dot. This is Hamilton's equations. It's partial of the Hamiltonian with respect to the action. This is one of Hamilton's equations.
Okay, cool. Thank you.
Any other questions? All right.
Is
There's no more-
this,
Yeah, another question?
sorry, yeah. Is this action, that's the same as the integral of LDT from classical mechanics?
Yes, well, this is a little bit tricky. We're doing time independent problems here because we're looking at the eigenvalue problem, finding the eigenfunctions of the Schrodinger equation. The integral of LDT is the integral of PDX minus HDT. Because the Lagrangian, the definition of the Lagrangian, or let's say the definition of the Hamiltonian is it's PQ dot minus L. And if you think about that, so you integrate LDT, it's the same thing as integrating PDQ minus HDT. So the PDQ part of it, Q means X here, PDX. So the integral of PDQ, that part of the action is actually a part of the integral LDT. The other part comes from the integral of the Hamiltonian times time. If we're dealing with this problem of fixed energy, that just gives us the energy E times time, which is kind of trivial, has been removed from this problem. If we were doing time-dependent WKB theory, you'd find that the phase of that really is the integral LDT. So the answer to your question is yes. Basically, it's yes.
Okay, interesting. Thank you.
Yeah, that's a good question. Later on, we'll do path integrals and we'll see integral LDT appearing there too. Classical actions. Any other questions? These are good questions.
So I know that we didn't really bother about what the size of the connection region was.
No,
But in general, just for an intuitive picture, what determines what that size of that connection region is?
it's a power of H bar. It goes like H bar to the 2/3 power, something like that. I don't remember the details. But when H bar gets to be small, the connection region gets to be small too. And that's why we can expand the classical potential about that region and get a good approximation, you see? Because the classical potential doesn't depend on H bar. So for H bar going to 0, anyway, one can analyze this more carefully and you can see that you have enough room in there.
Uh-huh.
You have enough room, you actually have enough room in there to get the asymptotic forms of the Arrhenian-Berry functions, which you need, you see, because you need to connect asymptotic forms.
Uh-huh.
Any other questions? All right. If not, then I shall stop share screen and I shall stop recording.